Next one is associativity. For associativity, for every x, y, z in G, x and then this operation with y, right? So we do this first and then we do the operation with z. This is same as x and then this operation y and z. This operation is carried out first, y and z, and then x is x and then the result of that. So that's associativity. The third one is what is known as, they call it neutral element. There exists an E in G such that, right, such that for every x in G, this x operated with E gives you x and E operation x also gives you x. Okay, this is called identity element in general. And then fourth one is the inverse element. Inverse element, for every x in G, right, there exists a y in G. This is there exists y in G such that when x and y are operated, they give you this E, right, where E is this neutral element, right? So x and operation y, or you can do and y operated with x is also equal to E. Okay, so this E is this neutral element, and then this inverse is denoted as x inverse, right, like this, x inverse. Okay, the inverse element is defined with respect to the operation, right, which is this operation, and it's not necessarily, this is not, so this is not equal to 1 by x in general, right? Right, it's equal to 1 by x only if this happens to be multiplication. Okay, this is not equal to 1 by x in general. Okay, so and then there is something called an abelian group, right? Now, so these four are the things required for this G to be called a group. Now, what is an abelian group? So for every xy in G, xy equal to yx, right? Y operated with x, or you take this operation and apply it to x and y, same as applying to y and x, right? Then this G is called an abelian group, or this is the property of commutativity. If you remember from school days, it's a commutative property. Okay, so that's the definition of groups. Now we'll look at some examples, right? So examples. This is example 210 for groups. Okay, so some examples are, so we have Z, which is the set of all integers, and addition. Okay, this is an abelian group, right? This is an abelian group. Why is, let's check closure. So I take two integers and I add them up, I'm going to get another integer, so closure is done. Associativity simply because addition is associative. So the neutral element is for addition is 0, right? You take any element, add 0 to it, you get the same element back, right? And then inverse element also exists, it's just simply the negative of, so for any x, negative x is basically the inverse element, because that will give you the neutral element, which is 0, right? And then it's also abelian because addition is commutative in Z, right? So that's why this is an abelian group, right? Now, so what they are giving next is n naught, which is defined as the set of all natural numbers union 0, right? And then you consider, so this is another example where they are defining this new set called n subscript 0, which is defined as the set of all natural numbers union 0. This is also sometimes known as set of whole numbers, right? And then we ask n0 comma plus, is this a group? This is not a group, right? Because the inverse doesn't exist other than for 0, right? Not a group, right? Not a group. Okay, so that's it possesses the neutral element because we added the 0, but it doesn't have the inverse for anything else. Okay, so then we do the next one is the set of all integers, and then dot is basically multiplication. Okay, so this is not a group, right? Because not a group because we don't have multiplicative inverse in Z, right? Other than for maybe +1 and -1, right? Other than +1 and -1 whose multiplicative inverses are themselves, right? So the neutral element exists. Neutral element is just 1, right? So that's there, but the inverse doesn't exist for anything but 1 and -1, right? So that's not a group. And then okay, so then what about the set of all real numbers then? This guy, right? Now this guy with respect to multiplication is still not a group, because in this case only the element, if you consider all numbers but 0, they all have multiplicative inverse as well, but 0 doesn't have a multiplicative inverse, so it's not a group, right? It doesn't have an inverse element. Basically 0 doesn't have an inverse element for this set of real numbers under the operation of multiplication. Okay, now then what do? We remove 0. Okay, so and consider R without 0, right, with respect to multiplication, right? The operation is multiplication. This one is a group, right? Is in fact an abelian group because multiplication is commutative. So that's easy. And then the next example is Rn comma plus, and then Zn comma plus, right? These are the so n is in natural numbers, right? So if you have, these are defined as component wise addition, right? So component wise addition, which means you just take these are n-dimensional vectors in real numbers and in integers. You take them, add them up, you're going to get another n-dimensional vector in the same set, right? And the inverse element also exists for both of them, because you just take the negative for each of the elements and add them up, and the all 0 vector becomes the neutral element, right? So that works. So these are both abelian groups, right? So these are both abelian groups. Okay, now finally we look at R m by n with respect to addition, right? And then again addition is going to be component wise addition. Okay, this is also an abelian group, right? Now let's look at R n by n with respect to dot. Now this dot here means matrix multiplication. Okay, so when we do matrix multiplication, we know that for one thing that not all n by n matrices have inverses, right? But let's check the other properties, right? So closure is there because you take any two matrices and you multiply, you get closure. You're going to get another n by n matrix, so this is fine, right? Associativity is fine, right, because matrix multiplication is associative. Neutral element is there, right? So neutral element is there, right, which is just identity matrix IN, right? So this is there, so there is no problem, right? But inverses don't exist for all matrices, right? If the inverse exists, then the A inverse is the inverse element of A. So what they are saying is a little bit interesting. So these three properties are all good, right? But if I just generally take R n by n, it's not going to be invertible, right? We've seen many examples where we know that not all n by n matrices are invertible. If the inverse exists, right, then we know it's fine. We can the inverse of A is if A is invertible, right, which is another one is the name is regular, right? A is invertible, then A inverse exists, and this also belongs to R n by n, right? So that's not a problem. So in this case they call, and in exactly this case R n by n is a group, n by n is a group and called general linear group. So it looks like they are taking the set of all invertible matrices in R n by n and calling it general linear group. Okay. Yeah, so general linear group is the set of regular invertible matrices. So this is given in definition 2.8 for general linear group. Is the set of regular or invertible matrices A R n by n is a group with respect to matrix multiplication. It's called general linear group. It's denoted GL NR. Okay, so this means n by n matrices in the general linear group. And then this is not abelian though. It is a group, right? So that's why it's called a general linear group, not abelian, because matrix multiplication is not commutative. Okay. So general linear group is the set of all invertible n by n matrices. Okay, that's with respect to matrix multiplication. So those are some examples. Okay, so we'll close this video here. We'll continue in the next video with section 2.4.2. Thank you for watching.